This is example 29 from 29.23 from another book. So in figure 29.23, a conductor rod of length L moves in a magnetic field of magnitude 0.450 Tesla. Okay, so this one I think I need to draw it out. The diagram is a bit too small. Okay, so this is the magnetic field. Then I have a conducting rod of length 30 cm. So the conducting rod, I represent it. I represent it with this black line over here, and this line over here has 30 cm. It's 30 cm in length. Okay, then it moves through the magnetic field of magnitude 0.450 Tesla. So the magnetic field is 0.450 Tesla, and it's directed into the plane of the figure. So it's pointing into the page. That's why it crosses in the diagram. Okay, then the rod is moving with speed of 5 meters per second in the direction shown. And for the direction shown, I believe it's in right angle to the rod right now. Okay, this speed here is 5 meters per second. Okay, now they ask, what is the potential difference? Huh? Potential difference? What is the potential difference between the ends of the rod? Okay, if you are moving the rod in this direction, what will be the potential difference between the ends of the rod? Basically, the potential difference here is equivalent to the EMF that you find. Okay, so it's nothing too special. It's just the EMF that you find. It's just that yeah, there's a jet flying over, jet plane or whatever. So to determine the EMF, it's just a simple thing. Again, EMF is just equals to negative d epsilon d phi over dt. So in this case, there's no number of turns, so you can just straight right away change it to BA cos theta. Okay, so here's the question right now. We know the magnetic field is constant, we can bring it out. You know you're not changing the orientation, you're not rotating anything, so the data should be the same. But here's the fun part, dA over dt. Where do you find the area? Where's the area in this question? Well, the answer is you have to imagine that there's an area over here. Okay, so what can you do to imagine the area? Well, you already have one side of the area already. Okay, now you can think of a rectangular area, but you already have one side existing in the diagram already. So what you need to do is just to bring out the other three sides right now. So the other three sides, you can draw it over here. I think that's fine. Okay, so you can imagine this as your imaginary loop. This loop here is imaginary, it's not actual. So you imagine the other sides to be on these three sides over here. Okay, it is also perfectly fine to, if you want to assume the imaginary area to be over here. It's fine. Okay, so let's say we do the orange situation and do the green situation separately. Okay, so if we follow the orange situation, then our EMF is equal to negative B cos theta. Then now this will be our length. This will continue to be our length. And this will continue to be our width. Okay, nothing too different from just now. You just need to imagine there's a loop over there. Then now you can just change your area to become length times width. So this time you can see that this rod over here is moving with a speed in this direction. So you will see that the area of this orange loop over here will increase because of this rod moving downwards. It will cause this loop to be larger and larger because this side is moving. So you can see the area is getting larger. Wait, the rod over here is moving in this direction, so it will cause the area over here to become larger and larger. Okay, but the length is remaining constant, but the width of this imaginary loop will get larger and larger as the rod moves diagonally downwards. You cause the width to increase, the length will remain constant. So if that's the case, the length is constant, we can bring out the length. It's B L cos theta. Then this one will be the change of width with time. Okay, we know that this change of width with time is just the speed over here. And since it caused the area to increase, it's a positive value of B. So negative BL cos theta, then it's a positive V over here. Then what will you get if you substitute in the value? Negative 0.450. The length is 30 cm, 0.300. Cos 0 degree, we take our area vector again to be pointing into the page so that the area and the magnetic field is in the same direction. So it's cos 0 degree, it become 1. Okay, then positive speed 5 meter. So if you calculate it, I believe you get the answer of negative 0.675. Okay, so this negative here is indicating the direction of the EMF, but I'm not going to determine the direction right now. I'm going to move on to the green, not green, it's purple, sorry. And then another loop is purple color. I'm going to move on to the purple loop first and find the answer first. Then after that, we only determine the direction together. Okay, so for the purple loop, the idea is still the same. The length is constant, but the width here is changing. And as you can see, if our rod is moving in this direction downwards, what will happen is the area, the purple area here will decrease. Okay, so this is different. If you pick it to be the orange loop, the area of the loop will increase. If you pick it as the purple loop, then as the rod goes like this, then it will decrease the area of the purple loop. Okay, so this is the difference in different place to choose the imaginary loop. Okay, so let's try to solve the problem. It's still the same thing. It's still epsilon equals to negative b cos theta dA dt. And you're still going to go through the same process. So let me skip the steps until the negative BL cos theta d width divided by time. Okay, but now you can see that the width is decreasing with time, causing the area to decrease with time. So dA dt here should be a negative value because the area is decreasing. So d width dt here should be negative because the width is decreasing. So therefore, you should expect a negative answer over here. That's why it should be negative of the speed over here. That's why what's the difference right now is if you pick the purple loop, then it will be negative V. So when you substitute in everything, it will still be similar, but you get an opposite sign for your answer. So you get positive 0.675 if you choose it to be the purple loop. Okay, you might think, is there a mistake here? Well, as I said earlier, the negative and the positive is for you to determine direction. So as long as it doesn't mess up the direction, then both of the calculations should be acceptable. So let's check whether it's true or not. So if we take the if you take the orange loop, the answer is a negative answer. So right now our area vector is pointing into the page. So if this is our area vector pointing into the page, then our turn will be a clockwise turn. But since you get a negative answer, it's the opposite of clockwise. So it means that the answer is anti-clockwise. You can write as 0.675 volt, and the answer is anti-clockwise. Okay. Again, if you use your right hand rule, your thumb pointing into the page, your curling of your fingers is showing clockwise. But because it's a negative answer, you flip the direction to become anti-clockwise. Okay? But if you move on to the purple loop here, it's positive answer. And you still pick your area vector to be pointing into the page. So if you pick your area vector to be pointing into the page, now your fingers is curling around clockwise and your answer is positive. So that means that your answer will be opposite direction. Opposite direction to the orange loop. Okay, I scared I'm confusing you all. But because it's a positive answer, then the fingers curling around clockwise, that will straight away be the answer. You don't need to flip the direction anymore. But the answer that you get for purple loop is clockwise. The answer that you get for orange loop is anti-clockwise. Now you might seriously doubt whether your answer is correct or not, because both of them give you the opposite direction. One is anti-clockwise, one is clockwise. They are totally opposite direction. So which one is true? Okay, let's try to think about it. Okay, I'm going to use an orange arrow to indicate the direction for the orange loop. So orange loop is anti-clockwise. So anti-clockwise will be turning in this direction. I might need to use a bigger arrow over here. This is anti-clockwise. Oops. Okay, you use your hand, go figure out yourself. This is anti-clockwise. Okay, for the purple loop, it's clockwise. So clockwise means you're going to turn like this. So what do you see? Do you see that on the rod itself, no matter you choose orange loop or you choose the purple loop, on the rod itself, the direction is consistent. Both of them is indicating the current is flowing upwards instead of downwards. The induced EMF is pointing upwards instead of downwards. Do you see that? So, as I said earlier, even though all these clockwise or anti-clockwise, they are opposite in direction, but remember, all these things are imaginary. You imagine it out from your imagination. So these are not real things. So you don't need to care about this portion of the thing. What you need to care about is only the actual rod only. And it is shown to you that both of these method allows you to determine the direction, and they are both pointing diagonally upwards. So both of them still give you the same answer. Okay, so you're free to choose which side you want to put as your imaginary loop. Okay, so if you go back to the question, what is the potential difference between the end of the rod? It's just 0.675. Okay, so I'm going to remove the clockwise or anti-clockwise, because that is not the important thing, because there's no loop over here. You can just say that the EMF is 0.675. Okay, so you can say this is the potential difference between the end of the rod. Okay, continue. Which point, A or B, is higher in potential? This is interesting. You can see that this is the direction of the induced EMF. So this will also be the direction of the induced current if the circuit is complete. But now the circuit is not complete. So what will happen is the charge will still move upwards, but you accumulate over here. So it means that if your current is flowing in this direction, then your positive charge will be flowing upwards. But now there's no complete circuit, so the charge will be accumulating near the upper part of the wire. So if that's the case, there's more positive charge over here at the upper right diagonal, so there will be less positive charge in the lower left diagonal. So positive charge is accumulated at the upper right diagonal. That will be the place with the higher potential. The lower left diagonal has less positive charge, so that will be the lower potential. So point A and point B, if you want to compare, this is point A, this is point B. Point B here has accumulation of positive charges, so this one will be higher potential. This one will be lower potential. Okay, by looking at the direction of the induced EMF, you can determine where are the charges accumulated. So that place will be higher potential. So point A is at a higher potential. Point A or point B? Point B is at higher potential. Sorry. Okay, continue. When the charges in the rod are in equilibrium, what are the magnitude and direction of the electric field within the rod? Okay. So if the charges are now accumulated over here and over here, then you can think of this part as like a parallel plate. This is the positive end, this is the negative end, and they are separated by the distance of L. So if you want to find the electric field, you use like your chapter 1 thing. And technically, this won't come in exam. Okay, electric field is delta V over D. Okay, so this is your rod, right? You know that the delta V between these 2 points be equals to the EMF, which is equals to 0.675. And you know the distance between this okay, the distance between these two N, it's how long is the wire again? 30 cm, so 0.300 meter. Okay, so this part is the positive end, this part is the negative end. Okay, so you can think of it like a parallel, like a parallel plate. This one is a positive plate, so it's a negative plate. The distance between them is 0.300 meter, and the potential difference between them is 0.675 volt. So to determine the electric field, you just take delta V, which is 0.675, divide by 0.300. Okay, so if you calculate that, you get 2.25 as the electric field. Okay, continue. The direction. The direction will be pointing from the positive plate towards the negative plate, right? So in this case, the direction will be in this way. This should be the direction of the electric field. Therefore, this is what we call as point A just now, right? This is what I call as point B, right, just now. So direction of the electric field, you can write it in terms of vector first. 2.25 volt per meter. Then the direction is pointing from B to A. Okay, nothing too complex over here. So we continue. When the charges in the rod are in equilibrium, which point A or B has an excess of positive charge? Well, that's point B, right? We discussed just now, positive charge will all appear near this corner. The negative side will be this place. So we can just say point B. Okay, B small letter. How many questions do we have? Okay, lastly, what is the potential difference across the rod if it moves parallel to AB? Okay, or you move directly out of the page. So what they are saying is, if you don't want, it's not working. So if you don't want the rod to be moving perpendicular to the length of the rod, you want the rod to be moving parallel to AB, so means like moving in this direction maybe. Or if you want the rod to be moving in out of the page, so let's say you're moving in this direction. So what will be the potential difference? Well, if you look at it, if you move parallel like this, you will not cut any magnetic field. If you don't cut any magnetic field, in this case, your motion here will not produce any EMF. Okay. If you want to think about it in terms of change of magnetic flux, how should I explain it in terms of change of magnetic flux? The idea is like this. If you continue to choose your imaginary loop to be like this, if you move your rod in this direction, this whole imaginary loop over here will be brought along in the same direction. Okay, so the whole loop here, that is the whole area of the loop here, is still experiencing the magnetic field even though you're moving like this. Okay, you're not expanding the area, you're not making the area smaller, you're keeping the area constant, and your area is passing through the magnetic field, and the whole area is still experiencing a magnetic field. So the B never changed and the A never changed. You're not rotating, so theta never changed. So there's no change in magnetic flux. Okay, same idea if you move. If you move out of the page, if you're moving the rod out of the page, something like this, the rod is now like this, right? You move it out of the page. If you put your imaginary loop, to be like this, you are bringing the whole loop in the magnetic field. The loop is not larger now, the loop is not smaller, you're not changing the area of the loop. You are just bringing the loop and follow along the direction of the magnetic field. Okay, means by the loop. Okay, let's say this is my loop. Okay, so I'm just bringing my loop, moving it out of the page. Okay, but still the whole page over here is magnetic field, so the whole area here is still experiencing magnetic field. So my B never changed, the area that is experiencing a magnetic field also never changed. I'm not making the area larger, I'm not making the area smaller. So the magnetic flux should still remain constant. Therefore, there should be no potential difference, no EMF. Okay, look at it from perspective of whether there's change in the magnetic flux or not. Okay, V equals to 0. Okay. You have to think through the idea a bit more closely. If you move the rod in this direction given in the question, only the area can increase. Okay, if you move it parallel to the direction of AB, then you not see the area increase. You are just bringing the whole area along. If you're moving out of the page, you're also bringing the whole area along. You're not making the area larger. Okay, so that's how you think about this question involving a single rod. A single rod is actually a changing area question. You just need to figure out an imaginary loop to begin with.